Okay, hello, this is Quinn Murphy reviewing problem number 4 on exam 3. So this is the one that I struggled with the most, I think. After going to lab and to lecture in Dr. Goldman's class, he kind of brushed on the fact that everyone kind of struggled with this one. So I'm going to do my best to review it, and I reworked through it, got a little more explanation, and some things that definitely would have earned me some more points the first time around. So just for the sake of, this is the diagram right there that I'm going to be talking about. I drew it a little bit bigger so we can see it when I start explaining what's going on, but I'm just going to go ahead and read the question. So a conducting loop is pulled out of an area with a constant magnetic field, B sub ext, pointing into the page. So that is why all those X's are there on those circles. The loop has a resistance R, a height H, and a length L, and is pulled with a constant force F at an unknown constant speed. So the first one, A, 5 points on the diagram, indicate the charge buildup on the conducting loop. And then it says, draw and label an arrow representing the net magnetic force acting on the conducting loop. All right, so the very first thing, so it says the charge buildup. So it's important to notice that on this loop in particular, you can see it here, that it's actually charged all the way around, but when they talk about buildup, they want it specifically at these two corners. So the positive is going to be on top, and the negative is going to be on the bottom. And then the next part of A says, draw and label an arrow representing the net magnetic force acting on the conducting loop. So our whole thing is moving at a constant velocity this way, which is so to my right, so right here. So then the net magnetic force acting on it is going to be in the opposite direction. So again, when I'm looking at it face on, that's to my left. When you're looking at it here on the video, that's to the right. The third part of A says draw and label an arrow representing the direction of the conventional current around the conducting loop. And again, if we look at it, because this top side is going to be positive, and we can tell that because of the force going into the page, so that is why they're X's. So the way I always like to think about it, if you have a dot coming at you, that means like the arrowhead is coming at you. If you're going into the page, and you're kind of seeing the back of the arrow, for if you follow that analogy at all. So with that, the loop is going to flow clockwise around our system, if you will. So moving on to part B. So those are all just things you draw on the diagram. And part B is right here. It says calculate the magnitude of the current through the conducting loop. Your answer should not depend on the velocity of the loop. So because we have it moving at a constant velocity in one direction, and then we have the net magnetic force moving in the other direction, then we know that F net for the entire system is going to be 0. And because that, I worked it out right here, but you can kind of see F net equals 0, and that is equal to F plus F mag. So F is the constant velocity moving in the plus x direction, and then in the negative x direction is the one that we assumed and drew on our diagram in part A. So you can set those equal to each other, and F is equal to F mag, which is equal to IHB, and it's H in this case because this entire length right here is L, but we're really focusing on just this segment right here, and that is labeled H in the diagram. So that will give you the value of the velocity of the loop using that equation, because the forces are equal to each other. And then in C, you have to use a few different equations. The first one being delta V equals E, what we know as EL, but in this case, L is just the arbitrary length of our entire system right here. And what we're really talking about is the H value that we talked about in the last problem. So it's delta V equals EL is the formula that we kind of know, but in this case, it's specifically delta V equals EH. So, and then delta V is obviously all equal to EMF, which is also equal to I times R, which also in this case is equal to F times R over HP. Let me see if I can get a good little footage of what we got going on right here. So relating all of those equations together, and then you can sub in for delta V and for IR, and you can get EH equals FR over HB. So obviously trying to find E, you're going to divide by H, and you're going to get an H squared on the bottom. And then the last equation you're going to use is E equals V times B. And so solving for V, in this case for finding the final velocity, the speed of the loop is V equals E over B. So again, we now know E, and we're going to multiply by 1 over B to find V, which is the speed of the loop, which is what we're trying to solve for in part C. So finally, after relating all those equations together, we're going to get that the velocity is equal to F times R, which is the resistance. So F the force times R the resistance over H squared. So again, that's the height of the loop, not the length of the loop, and then times B squared. So again, our final answer for the speed of the loop is V equals F times R over H squared times B squared. So hopefully that clears it up and kind of walks through this problem number 4 for you. I think a lot of people missed some because there was a lot of all or nothing on the grading key. But for me, it was definitely relating the formulas and being able to review those that was beneficial in making this video. So thank you very much for watching, and I appreciate it very much.